Well, you know, it's a long tradition beginning with Galileo in 1610 to build an instrument to discover things about the universe. This is just the latest step of many such steps that Caltech has actually been in the lead. The Palomar telescope with 200 inches or 5 meters was the world's largest telescope for 4 decades. It was in the early 80s that we realized that there would be a new generation of telescopes with a new technology that we joined with the University of California, formed a team to build this more larger next generation telescope at the time, and we built 2 of them. So we have 2 such telescopes, which are currently the world's best telescopes, ground-based telescopes. But that technology, we knew at the time, would be one that we could expand to even larger scales. And that's what we started doing 10 years ago in the case of the 30-meter telescope. Turns out if you want to build a mirror that's 10 meters in diameter, it's not a single piece of glass, it's a set of segments, 36 hexagonal segments like tiles on a floor. If you want a 30-meter mirror, nearly 100 feet in diameter, you need 492 segments. And those all have to be controlled by a computer so they maintain their alignment to each other to within a millionth of an inch. So it's really we know we can do it because we've done it with the Kex, but clearly this is a technological tour de force to build such a thing which has that kind of precision as you point it at different places in the sky. Well, with a mirror nearly 100 feet across, it will have unprecedented resolution of the distant universe and also the nearby universe. That means we'll be able to see the first stars that formed in the universe and the first galaxies as they formed in the universe. And we will also be able to study planets around nearby stars in the Milky Way galaxy. A 30-meter telescope is 3 times the diameter of the Kex, which are the world's largest today. And that means it will have a 3 times finer angular resolution, pixels if you like, in terms of your television set. So a high definition, a high spatial definition with the 30-meter telescope, at least factor 3 better than the Kex and much more than that than other existing telescopes. And that means that we can see things that are not really seeable with the current generation of telescopes. Looking back to the beginning, when the first stars formed, they were very far away and very dim. And it takes the large area of a 30-meter telescope and its angular resolution to be able to find and study those objects. The instruments on a giant telescope are also giant. So each of our instruments is room-sized, and they're mounted on the platform, rotating with the telescope as it orients to look at different stars. On this telescope, we will have a mirror which will reflect the light from the main mirror onto the side where the instruments are and can point from one to the other very quickly. So if we decide we want to make a different kind of observation, in 5 minutes we can switch the light beam to shine into this other instrument. We don't move the instruments, we actually just move the light beam into where the instrument apertures are. One of the key things for these modern telescopes is something called adaptive optics, because even at the best place in the world, there's still turbulence in the atmosphere and the stars still twinkle, which means they're jumping around. We now can, in fact, correct that so that they're perfectly stable, and that also gives us another factor of 9 in capability, because we not only have 9 times more light because of the bigger mirror, but that light is focused in a spot of 1/9 the area. So per unit area, it's 81 times more sensitive than the Kex, which are currently the most sensitive telescopes in the world. Well, one of the frontiers, there are many frontiers in astronomy. Certainly one of them is to understand how the universe became what it is today. It looked much different in the early days. The stars were different, the galaxies were different, and we will now with TMT be able to really understand and observe what things looked like 13.4 billion years ago, shortly after the Big Bang. But nearby, of course, there are many, many planets now around other systems, and the capability of the TMT will be essential in looking for and understanding the nature of those planets and whether there are any possible places for life to have evolved elsewhere in the Milky Way galaxy. It's usually the case that the most important discoveries you make with a new instrument are something that you didn't even know was there to be discovered. That's what makes it so important, because it's not just understanding better what you already know, it's really telling you something you had no idea was out there. So I really believe that with this kind of a capability and this factor of 81, that the opportunity for these unexpected and important discoveries will be quite rich. This is the first time that this has happened, I think, in optical astronomy, where a project of this size is both private and public and international. And that was certainly one of the challenges, and will continue to be the management challenge we will have as we bring all these things together from around the world and install them on the mountain. We did a survey of sites in Hawaii and in Chile and actually in Mexico as well to look for the best site. And we settled on Hawaii some years ago now after an extensive study, and then spent a number of years getting ready in terms of getting permits and subleases. And all that's in order now, and that's the reason we can actually have a groundbreaking, which kicks off the construction of the 30-meter telescope. The groundbreaking will take place at the site on Mauna Kea at just almost 14,000 feet elevation, and it will have a groundbreaking in the sense of using o'o sticks, which are the Hawaiian way of digging at the ground. And there will be all the partners in the observatory will be represented during this groundbreaking ceremony, and ribbon cutting and a Hawaiian blessing. So it's all done at near freezing temperature. We hope it's not too windy on the side of the mountain. We expect to begin to start taking data in the early part of the next decade, in the early 2020s. So it's a big project, so it takes that long just to put it all in place and put it together on the top of the mountain. As you can imagine, after 10 years of getting ready, it's really exciting that it's happening because it has been a long development period to both do the technology development and do the governance partnership involvement. So there's a lot of excitement that this is a key step, obviously, to begin construction. And even though it will be early part of next decade, at least that the clock will have started.